So listen, this is what I've got planned for you guys today. First of all, welcome, right? And as you remember, my name is Michael Rees. I'm a professor here at Paterson University. My primary focus is sculpture and digital media, but I'm also co-director of the grad program, and I'm also the director of the Center for New Art. The Center for New Art used to be called the Center for Computer Art and Animation, but since Apple Computer took computer out of their name, I thought we could take computer out of our name. New art implies, though, on some level that we're going to study and work with new media, okay? New media being things on the computer, interactive design, 3D modeling, that kind of thing. The center is kind of an exciting place, and I was really happy that the ed program and Dina, say your last name again, I'm sorry. Skiketti. How's that?
Yes.
Yeah, Skiketti. All right, there we go. Invited me to participate, right? Because the center is really designed to be a place where, as a resource for people like you know, educators in the region and professionals and artists to get together to study the effects and the potentials of these new technologies on contemporary life. That's exactly what it's designed to do. So it couldn't be a better scenario. And in fact, I've kind of, I just want to show you that later I'm going to email you the mission statement and our vision statement so you can get a feel for who we are and what we do, all right? Now today what I'm going to do is this. We're going to have about half an hour now where I'm going to make some introductory comments. And then what we're going to do is do a tour of the whole facility for another half an hour, 20 minutes, something like that. I'm going to show you the rapid prototyping room, the CNC mill, the 3D scanner, etc. Then we're going to come back into this room. We'll take a little break. You know, you can talk a little bit and get to know one another. Oh, you already know each other, don't you? Well, I'll get to know you. That's the way it'll work. And we'll take a break. And then come back in here and I want to show you a group of videos which will be very informative about what 3D printing is, how people are experiencing it in culture and so on. And then we're going to end with kind of a show and tell. I've invited Jeff Flash, who is a teacher at Kinnelon High School. I don't know if you guys know where Kinnelon is. I've never been there, but I trust that it does exist because, you know. And Jeff he's also a grad student here at the university. So he's been getting his MFA, and his focus has been on sculpture and digital media. And then we also have some students, Ashley Simon and Brian Sandylands. Ashley's an undergraduate student, very accomplished. She is one of the, you know, I don't want to say too much because she'll get really mad at me, but let's just put it, she's one of our most accomplished students. And Brian is a grad assistant that just joined us this year, a graduate of Rutgers with a history degree and a dual major in art. And so, we've got a great crew here for you. And then a little later, hopefully, two more people are going to join us, Nicole Krisbacher and Sam Chuck. So I've prepared kind of a big day for you, all right? There's a lot of information in here. Now, if you've put your email down and it's correct and I can read your writing, you'll all get an email with all the links of all the things I discussed today, all right? All right, good. Now, just to kind of get you located once again, all right? What do? I am not from the digital generation, right? I wasn't born knowing how to do this. I'm like many of you, I was born doing all kinds of other things, working with my hands and doing all this stuff. I consider myself from the bridge generation. And I'm one of the people that has embraced the new technologies, at least to the extent that I study them and use them in my artwork. I've been doing this for a long time. The first computer-aided things that I did were in the early 90s. I made my first rapid prototyping piece in 1995. And so I've been doing this for a really long time. I'm one of the first sculptors in the world to use this technology. Again, I'm just giving you a little background. I don't want to, go on too long about myself, but I was in the 1995 Whitney Biennial, and I was also in the 2001 Bitstreams exhibit, which was at the Whitney Museum again, which was the first exhibit, one of two exhibits. One was at Whitney, one was on the West Coast at San Francisco MoMA. And that looked at artists using digital media. So I am like a ground zero person. Even though I'm not a digital native, I'm a ground zero person when it comes to 3D modeling and digital media, all right? And so that's kind of an important thing to keep in mind. I'm enthusiastic about it. One of the reasons that I thought was fantastic, and I saw immediately from the very beginning, is that if you could use the software, you could print whatever you made in the software. And the implications of that were enormous from the start, right? In other words, as an artist, I could get a hold of the same equipment that a high-end engineer would use at any corporation or company in America if I had the software, right? Now, when I first started with this stuff, I mean, typical digital media sort of thing, the software and the hardware were $100,000 for the pair. And the machines that made these automatic models were $500,000 and so on and so on. So only big corporations could afford to do it, right? And of course, now we're at the point where I can have all the same software, all the same stuff on my laptop, nothing terribly special there, just a regular old laptop. And I can buy the machines or rent time on the machines, and we're going to talk about that a little bit more. Because not only, for you guys, I know that budget is a huge issue. You know, having enough money and all that sort of stuff to do things is a big issue. But I just want to point out to you that now, where it used to be a very rare thing, and it was, maybe, so on and so forth, now it's very widely available. You can go to websites and do various things on different places, order up parts. You can actually even design parts on the internet. And those parts can be saved, and then you can do it with all kinds of digital manufacturing. So what are we talking about today? We're talking about three basic things: input, processing, and output. That's essentially what we're talking about. And that's what computers are good at, right? People like to ascribe a certain intelligence to computers. I don't like to ascribe any intelligence to computers. They're non-intelligent. They are right now an organized series of switches. So we work programs that flip those switches. That's what we do. So what we see here when we look at it, and I say this all the time, is we see an enormous and beautiful utopian representational system. All right? Now you say, what the heck are you talking about? Utopian representational system. What I mean to say is that the way computers represent information is not necessarily the way the world works. Right? And one of the things that we're experiencing is all of humanity trying to cram themselves in to fit the computer. If I were to give them an image of that, rather than standing here on my 2 feet like this as a natural human being, this is me without a computer. This is me with a computer. Okay? And I want to make that really clear. And it's the company's intention to make you go like this, right? Check your email, put your website up, have a blog page, and it just goes like mad. Twitter, Facebook, Tumblr, so on and so forth. It goes like mad. So the point is that I'm suspicious of computers as much as I'm for computers, right? I think they represent all kinds of problems for us. And one of the reasons I know that maybe you guys, critical thinking isn't your primary goal, but at the university, critical thinking is extremely important. And I introduce this into my classes at an early level, right? I want people to be as wary of the tool as they are enthusiastic about using it, right? All right, good. So input, processing, and output. Input. Now, everybody in the room has taken a camera and imported it into a computer. That's essentially input. There are all kinds of input. A mouse is an input device. A keyboard is an input device. A tablet is an input device. With 3D, you have one major input device, and that is a scanner, a 3D scanner. And you can take pictures, which is done by laser. I've got one here. We won't go into the great details, but just trust me. The laser comes across, and the laser is kind of like, it's a little bit akin to an Egyptian box. Does anybody know what that is? Have you ever heard of that? In the old days, when the Egyptians were making big models, they'd make a model out of clay, and they'd put a box around the sculpture, and the box had a grid on it, and they'd take a rod and they'd push it in, and when they hit the piece, they'd call it out. And then the sculptor would sit there with a drill and drill in that far. So there was that's how ancient this idea of taking a small model and making a big model out of it, right? Now, what the laser does, the laser is akin to the rod going in. The laser hits the piece and it measures it. It says, oh, that's 3. Now, it's doing it so fast and so completely that it's building up this surface, all right? So and it makes a 3D model. And the 3D model can come into the computer, and now we're talking about processing. Now, there's other ways to get 3D models. They're available freely on the internet. There's a place called Thingiverse and so on. There's all kinds of repositories, a little bit like YouTube, if you've been to YouTube, where people are sharing videos of their experiences and doing all this stuff. So there's 3D places like that as well. Once it's in the computer, you can use two different general categories of programs. One category is engineering, mathematics, architecture, industrial design. And the other one is animation, art, sometimes architecture too, because that's kind of the crossover thing. Sculpture, movies, all that kind of stuff, right? At the very bottom, that code is all the same. But the way they put an interface on it differs, right? So an engineer needs something different than an animator does, all right? Now again, there's places where they intersect. I don't know if you remember a few years ago, Dodge had a car commercial where the car sort of disappeared and the motor was in there working and then it came back. Well, that was all animation, but it was based on the engineering data. So you can see that these areas are folding over each other. And my brother informed me recently that that time-honored thing that I used to believe in, the right brain and the left brain, has been discredited. They say that it's discredited now. So anyway, I used to always say, see, we're blending the right brain and the left brain together. We've got a scientific, kind of a scientific or engineering or math-based kind of experience, and then we have the art-based experience, which for STEAM is exactly what we're talking about. And the thing is that's interesting about I just want to put this in, I'll talk about it a little bit further. When you use these programs, you're literally using geometry and living in geometry, I call it inhabiting geometry, in a way that's intuitive. Like for example, if I explain to you that in the world there's an axis in the center of the world, there's a ground plane, each object has an axis within it, that axis is related to the ground plane, blah, 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 blah. You guys are like, please, I'm not engineering oriented, right? I could go on and on like that, and my students do. I watch them go like this all the time. I'm an artist, what are you telling me this stuff for? It's like, they're doing it now. They're doing it right now as we speak. I watch them do it all the time. But the truth is when they get their hands on it, and they rotate, and they zoom in, and they move, and they all of a sudden understand it intuitively. It's as if, it's like understanding your own body, Now, it's a little bit abstract. I call this mediation. It's a little bit mediated. You're not in the computer, you're looking at a 2D, but now we can process. Now, again, I'm not going to talk about the engineering and the math and the architecture and the industrial design. That's not what I do. I do more the art side, movies and animation and all that sort of stuff. And that's what we teach here, right? We primarily teach that. But these same skills, and if these same skills can be used to make art or to do engineering. They're the same skills. That was what was so exciting to me, that I could get a desktop printer that engineers had and use it as an artist, By the way, in the early days, I wrote a bunch to get a hold of the technology because it was so expensive. I became sort of notorious in that world, that engineering world. I mean, they hadn't met many artists, and I was writing articles about it and saying, this is how you could use it. You could do this, you could do that. You could use it in movies and then make the car. You could make a 3D color print. And they hadn't heard of that, and 2 years after I wrote the first article in Rapid Prototyping about color, they came out with a color printer, right? So as an artist, I realized immediately that it needed, so you see, we're working together. These two sides, these two cultures, C.P. Snow, I don't know if you all read that book, are working together. All right, so now we're processing. What can we do when we process? Well, we can do some more design. We can push and pull, kind of like digital clay. It's not really digital clay, but they call it that for a metaphorical reason. I can understand it. It's different. It's a new technology. It behaves differently. You can push, pull, do that stuff, but you can also do other things. You can render a picture, and that picture can be used for all kinds, any purpose that a picture could be used for. Visualization, advertising, as a work of art in and of itself, all that sort of stuff. You can make animations from this. So we could just do simple rotations of the object. So we really see the object when we post it on the internet, so on and so forth. Or, what did I say? You could, or you can actually print it. You can literally take any design that you can make in one of these programs and you can print it. Now I've got examples. Please contain yourselves. Don't jump up all at once. You're going to have a chance. Remember, we got the show and tell at the end. So you'll have a chance to hold these things in your hand and see what we're talking about. But it's not science fiction. The first company, the first low-end commercial company called these things replicators. And I think there's a couple of people in the audience old enough to remember Star Trek. All right, they were called replicators, right? Give me a cup of coffee. Well, we can't make coffee, but we can make the mug. We can do that now, right? We can absolutely do that now. And you know, the other thing is, I don't remember if you guys, I wonder if you remember watching that Apollo astronaut film. I forgot what it was called. And remember they have a problem on the thing and they're trying to cobble together the part, right? So they can get back down to Earth. Well, one of the, one of the ways this idea was sold to people is that you could have a machine on board of a ship or a spaceship or something like that, and if the part didn't work, you could call up the database, find the part, and print it, and when it was done printing, install it back into the piece. And so that's one of the uses for this technology. So you see how fantastic, right? How fantastic. This is a place, it really truly is a place where art and science, or art and engineering, whatever, art and math can live together, where they absolutely be together. All right, so that's the processing part. And then the output part is it can go to this 3D printing, or it can go to CNC milling. Now, just to remind you, 3D printing prints things one layer at a time, one on top of the next until the object is finished. And it uses a variety of techniques to do it. We're gonna see some images and some animations and all that sort of stuff of that. So, input, processing, and output. Now when I prepared this for you guys, I realized that this is going to be a lot of information for you. That's one of the reasons that I took the time to make sure that you have all the links. So anything I talk about, you can go back to and you can study a little bit further. I'm not 100% sure how this is going to fit into your curriculum. I've never taught 7th to 8th graders. In fact, I bow down to you because I can't talk to 7th or 8th graders. Oh, 5th graders, 5th to 7th graders. I bow down to you because I don't know how to, I have enough problem with these, these 20 to 20, 18, 19, 21-year-old, I don't know how you do this, right? But I thought I would really put out for you a cornucopia of stuff, and you can pick and choose within there what you like. And as we work further, you know, maybe we can also collaborate. You can say, well, can it, you know, be, you might, you know, we'll have a conversation, a real conversation. Now, are there any questions at this point? Do you want a little clarification or anything like that? All right, good. Now, how are we doing? We're about 1:20. Wow, I'm going faster than I thought. All right, so let's do this now. I feel we'll just go ahead, and this is something you can't put on film, but I'll go ahead and I'll play this video. Now, I want to introduce this company a little bit. It's not a company, actually. It's an educational association. The guy is a professor at the University of Bath in England, all right? I probably got that wrong, but you know, he's a professor in England somewhere. And what he did was he created this thing called RepRap, and RepRap is some short replicator rap, or I don't know exactly what it means, but we can read that and find out. And basically his idea is he wanted to make a machine that could make itself. He wanted to make a machine that could make itself. And so he came up with this idea of the RepRap. Now there is a prior machine that did that, and that was part of his inspiration, but there was another part, and that is that he wants these machines to be biological. He's using biomimicry as a concept, so people can, develop machinery and software that'll make itself. Now, there's actually a lot of problems in there. Hardware, software, electronics, electricity, there's a lot of problems. He can't make, at this point, not yet, they can't replicate electronics by themselves. That's something that a lot of humans have, it's very complex. They can't put the thing together, you know, of course they could design a robot and whatever, but that's his goal. And the other goal, the other idea of the goal, was to make something that was incredibly affordable for anybody that wanted to study or work with rapid prototyping. So basically you could buy the parts for a kit for about $500, and you can assemble it. And you know, if you're geeky that way, which by the way, I doubt you guys are, I can tell you I'm not. I don't like to do that kind of thing. I don't like to tinker and, oh, it doesn't work. I want stuff that works. I want to buy it and use it. That's what I want. I don't want to mess around with it, all right? But I show you this because this is huge. This was a huge movement in rapid prototyping, and it spawned the new low-end RPs that are under, you know, right around $2,200. So I thought it would be good to, now let's hope that the speaker works. Let me just, I thought it'd be good for you to show this sort of intro video, in part because also I have to say, it doesn't look like it showed up. Headphones. Huh, well, let's see if it works.
We print documents and photos from our computers daily.
Most of us in the developed world effectively run a home printing press and a home photographic lab, courtesy of this technology. Suppose you could plug a 3D printer into your computer. This 3D printer makes solid, strong plastic goods from designs that you've created yourself or that you have downloaded from the web. You could make lots of useful stuff that, at the moment, you have to buy. In effect, you would be running your own factory alongside your printing press and your photographic lab. There's nothing new about 3D printers. They have been around for almost 30 years, but all the commercial ones are very expensive. They typically cost about €20,000. This is the RepRap 3D printer working. You can make it yourself, and doing that will only cost you around €500. What's more, following the principles of the free software movement, the designs for the RepRap machine are being distributed to everyone free under the GNU General Public License. And here is the really clever bit. Those designs include all the plastic parts for the RepRap machine itself. So, if you have a RepRap machine, you can print a new one for a friend. RepRap was thought up by Adrian Boyer at Bath University.
I started the RepRap printer by a biomimetic analogy. That is to say, an analogy taking an idea in nature and putting it into engineering. The object in nature that I copied was the phenomenon of symbiosis. In particular, if we look at the symbiosis between the insects and the plants, which has been running for 130 million years since the late Jurassic, that is an incredibly successful and stable symbiosis. And we all know how it works. The plants need to pollinate each other, but they can't move, so they make nectar as well as pollen. The insects visit the plant to obtain the nectar, and in doing so transfer the pollen to the other plant. The insects get a meal, the plants get to reproduce, everybody's happy, both species benefit from the relationship. The RepRap printer is intended to be exactly the same, with people taking the role of insects and the printer taking the role of the flowers, because the RepRap printer doesn't just copy itself, it also makes useful goods. And those goods are the equivalent of the nectar, and that nectar, those goods, rewards the people who assemble the machine, because those people are helping the machine to reproduce in just the same way that the insects help the flowers to reproduce. The RepRap printer works by melting plastic and then building it up into three-dimensional objects which solidify when they cool. It starts with a filament of plastic about 3 millimeters in diameter, rather like a piece of wire. And that filament is fed into a melting head in the machine and then extruded out of a very fine hole. The machine then scribbles with that molten plastic onto a flat plate to make a layer of the object that's to be built. The plate then drops down by a small fraction of a millimeter, and the next layer is scribbled on top of that, and so on until the whole component has been built in 3 dimensions.
Vic Oliver from New Zealand is another member of the team.
I just love the ability to design something, have it made right there on my desktop, and then realise I've done it wrong, correct it, leave the thing printing, come back in the morning and there it is, perfect and glorious.
There are 16 people in the core RepRap team from all over the world, and many others who help informally. The writing of the software and the documentation is done by this collective, as is the design of the electronics and mechanics. All the software, documentation and designs are published and shared on the web using wikis, blogs and SourceForge. Ed Sells is one of the principal people involved in the mechanical design of RepRap.
One of the key challenges to designing the printer is to design it in such a way that it can make its own parts. For the first version, if we do a simple part count analysis on the design, we find that it can make about 50% of its own parts. As we develop the second version, which is what we're currently working on, we hope to improve this ratio to bring the number of parts that it can make for itself up. We hope to do this by developing new deposition heads so that we can print in new materials and increase the functionality of the printer.
In May 2008, RepRap achieved replication for the first time. This parent machine made a complete set of parts that were then used to build this child machine. The child machine was immediately put to work making grandchild parts. The team are now working on version 2 of the RepRap machine. Version 2 will, of course, be printed by version 1, as well as being able to print itself. Version 2 will allow a wider range of materials to be printed, including electrical conductors, so that the machine can make its own circuit boards and other electrical products.
If RepRap's successful, a number of changes may well happen in society. The principal one of them will be that we have the distribution of the manufacture of goods. At the moment, economies of scale mean that it's sensible for goods to be manufactured in factories and then to be shipped to individual people who wish to have those goods using a complicated transport system. If RepRap takes off and increases its abilities by evolution to manufacture more and more products, then people having these machines in their homes will mean there will no longer be a need, or no longer be such a big need, for factories to make the goods that they want. When they want something, it'll simply be a question of downloading it from the web in the way that they currently do with music or a film or anything else, and that downloaded file would then allow them to manufacture whatever object it was that they wanted in their own home. No transport involved, except for the raw materials, which have to be transported anyway, of course. And thus we have short-circuited a large part of the conventional supply chain for material goods to individuals.
Then you can make one for your friend, and then there are 2 RepRaps, and then you can both make more RepRaps for more people, so it goes exponentially. There are 4, 8, 16, 32, and before you know it, everybody in the world's got, who wants one's got a RepRap, and nobody can hold the monopoly, so it keeps the cost down.
Chris DeBona, open source programs manager at Google, said, "Think of RepRap as a China on your desktop." And Sir James Dyson, inventor of the Cyclone bagless vacuum cleaner, said about RepRap, "Advanced fabrication technology that can copy itself is a truly remarkable concept with far-reaching implications." The objective of the RepRap project is to give away the designs for a machine that anyone can use to make many of the goods that we all currently have to buy. And anyone can also use their RepRap machine to make more RepRap machines for other people. The project aims to put a factory in every home, a factory that can make more factories.
So that's pretty tall order, isn't it? It's pretty cool, isn't it? Did anybody have any inkling that this was going on? No. Well, it's been going on for about 30 years. It really has. And these ideas, even though they've come to fruition now, the reason we're hearing about them now is because they're affordable, right? $500 or $2,000 or $3,000. You can now buy a very capable rapid prototyping device for that amount of money, right? So it's got to the scale that a large number of people can adopt it and use it, right? Now, what I love about this is that, on some level, is that this has been developed in education. This is not something that, I mean, the big companies, hopefully they made their money because they're gonna have some challenge, right? To be able to produce these kinds of machines. Now, of course, they're always gonna be leading edge and going for more and more and more complex things. But by the way, how many of you would like to, I beg your pardon? Oh yeah, I think it's working. I think it's helping a lot, yeah.
You don't hear about it.
Well, you know, the thing is that now that you've been exposed to it, I bet you that if you open up your mind and your antennae, you'll start seeing it all the time, everywhere, right? Just because, you know, you came here and you're looking.
Wouldn't this be small manufacturing
Yes.
without having enormous plants or something, and really focus on a specific, whatever it is,
Yeah.
to fit into some other thing?
Well, you know, Jeff and I both have real world experience. I've run companies, I've been in companies, and I've also been an educator and an artist. So I have this broad experience. Jeff too. We've both been model makers, and we worked in industrial design firms where we used to build models by hand and try to prototype them. Now, when this technology first, when this technology first came out, here's the way it would work. Somebody would take clay or some similar material, they would make the form of an object, they would mold the object, actually not even mold it yet, They might pass it around, make some design iterations, etc. Then they, if they liked it and they were ready, they might mold the object and then make 3 or 4 versions. But those were really form studies. They were never function studies, right? They might be form or fit, but not function. With this technology now something had to change. People had to stop being sculptors and start being digital sculptors, right? You have to be able to use the software to make this work, right? But so that was a shift. And what's happened now, though, is that same process that used to take weeks and weeks can take days, right? You can design something and work on something. So, you know, from the engineering or from the business standpoint, this is a boon. This is a total boon. Now, for certain kinds of products, you know, for example, this does very well at making things this big. It's a little more difficult when you want to make something this big, or the size of a car. Sure, and I'm going to show you a different technology, very similar, but a different technology.
Now, with this type of technology, does it eliminate jobs or create jobs?
Well, I mean, I personally think that it's going to create jobs, but, you know, don't believe me. You know, don't believe me. Well, I'm not an economist. You know, the thing is that right now, if you were going to bring a product to market, right? Let's say 5 years ago, something like this. You're going to bring a product to market. You might have done some CAD work and then have them printed with the machines and done some tests. But then you would send the whole thing to China, and they would do the injection molds, and they would send you back the parts, and you'd sell it. Now, it's not quite there. It's not quite there. I don't want to be, you know, again, I told you, be as suspicious of technology as you are optimistic about it, please. I mean, I really encourage you. Maybe a little more suspicious, a little less optimistic. But right now, you're able to, you know, we're almost able to actually manufacture the product directly out of the machine.
So who designs the software? Artists? The engineers?
The software is done by companies that want to sell that software to you. But I have a whole list of softwares that are completely free. I mean 100% free. In other words, I wouldn't have invited you here today if it cost $5,000 to buy a license for the lab, because I know you guys, you know, you're not going to be able to get, you know, maybe you get a grant or something. But there's software, and I've taught software in university classes that was free. So these are competent professional pieces of software. You know, they may not be as up to date, or the icons might not look as sexy, or, you know, something like that. But these are very powerful, very strong, and as I mentioned to you, there's now a browser in, a CAD program in the browser that you can use, and it's free, 100% free. All right. Now, again, you might want more, you might want less. I mean, you know, you guys are the ones that are going to determine what's appropriate. But I tried to find the simplest, most basic browser. Now, I know a lot of times you're trying to design, like you showed me a couple of things, you know, what's an obtuse angle, what's an acute angle. I think you can do those kinds of things in the browser-based thing, right? The browser-based CAD software, right? For example. But the other cool thing, and you got to admit this is totally cool, is you can make a robot. You could have every kid in the room design a robot, and they could have little snap-together parts, and you could explain this whole thing, and you could build that thing in the room. And, you know, look, it takes 5-6 hours to build one of these robots, but let's say you can build 3 robots in 6 hours on a bed, and you got 40 kids or something like this. So that's how long it's going to take you to get through all the robots, right? That's, you know, it's not. So in other words, but, you know, if we got a great grant from the Dodge Foundation, maybe we get a wall of these things. And at the end of the day, they're all the robots for the kids to take home and play with. They're making their own toys. And they go home and they're holding their toy in their hand and they say, I made this at school. This is what I did. I mean, you know, yeah, they won't believe it. They'll say, you're lying.
Now, with the toy that is being made, will that be animated, or that would be a whole new process for the inner design?
The animation, you know, look, as I mentioned to you, you have the input, the processing, and the output. Part of the processing is doing the animation. That's a whole skill set in and of itself. If we want to talk about division of labor, you know, animation is not impossible. Remember we all did flip book animation, that kind of thing? That's fun. You know, that's not impossible, not difficult. And I can make quick little, you can do quick little animation kinds of things, but I don't want to oversell this. Animation is as difficult to do as this. All right, so you get the idea, you know, that there's you know, maybe one of you really loves the animation, you want to do the animation, and one of you really loves the modeling, you want to do the modeling, you know. So you break it up in such a way that it works out that way, you know. All right, now good. So now you got an idea, right? You got an idea. Now I like that guy Adrian Boyer, and I like his idea about rapid prototyping and factories that make factories and all that kind of stuff. And I think that we've noticed in computer revolution that these things make themselves over and over again, and it works pretty well. In fact, I just read that 1 billion people have smartphones in the world. That's 1/5 of the people on planet Earth have smartphones. That's mind-boggling, right? That's mind-boggling. So I really don't, I think it's a matter of time before we use these things, we have these things, and they reach great economies of scale. All right, so we have a little introduction. Let's spend some time to look around in our environment here, and let me show you a couple of the machines that we have right here on the spot. And let's see, and then we'll do that for about half an hour. I'll take you to one room, I'll take you to another room. You're able to see the gallery. We'll go in the annex gallery, and you can kind of get a feel for our facility and what we do here. And then we'll come back and we'll watch a couple more videos, all right? All right, good. And what we have in here, you know, computers are everywhere. We have a 3D scanner. This is what I mentioned to you. This is like the Egyptian box, right? And let's see here. Well, the best thing to do. So you can see that it has a lens and a laser. The laser goes and it makes measurements and tells us how far it is from the thing. I have to say that of the technologies that we, by the way, this is maybe 2007 or 2008 technology. Now there's a company called Autodesk that's come up with these 123D products. That's what they call them, 123D. And they have a way where you can take photographs, 40 photographs around somebody's head, load it up on the internet, and they'll send it back on. So they've completely gotten rid of, now, I will say this is precise, this is industrial, this is commercial. That isn't commercial, that's more art, or, you know, it's a little funky, it's a little marshmallowy and all that sort of stuff. But again, I mean, how exciting. You can almost do portraits of people and load them up. And I'm going to show you a little bit later, there's some programs that you can use. So that's kind of I've never liked that so much because that's the input part. I love working directly in the computer. And so in that sense, that's what I love to do. That's what I taught myself to do.